So thanks a lot for the invitation. It's a pleasure to be here for the second time at this nice international conference on fracture. I will talk today about the role of finite temperature in fracture propagation in some materials, essentially in fracture in fibrous material, namely paper. And then a little part will be also on the role of finite temperature in fracture in interfacial fracture. So the title of the talk is How Cool Are Cracks? A burning issue for paper, because as you'll find out, we found something we did not expect looking at fracture in paper. The people with whom we have done this study is, so Olivier is also from Strasbourg. Tom and Muriel were students of first year of master or bachelor that did a part of simulations. Stefan is he's a scenarist researcher at Arrhenius, and the experiments were done when we were visiting Knut-Jürgen Molløy in the University of Oslo, together with him. So the reason in general why we are interested in looking at the importance of temperature in various fracture processes is that we had already studied interfacial fracture in a number of things, in setups like the ones that Daniel presented some days ago. But we found out that looking at the slow motion or relaxation of fracture in PMMA, there was a creep activity. There was a subcritical crack growth going on forever, with cracks slowing down if we just exerted a certain elongation on the sides of a crack and waited with this fixed elongation. So we wanted to look a bit if there were activation processes which are governed by an Arrhenius law, like many activation processes. So something where typically the velocity of the crack, as in a chemical reaction, would go as where a frequency nu go as a characteristic frequency nu zero, characteristic of a molecular vibration, times an exponential of, and then a Boltzmannian with a gap. With a gap in energy here over Boltzmann constant times temperature in Kelvin. And there you can see delta G as being an activation energy of the fracture minus the energy release rate if you need to pass over certain pinning thresholds which are at GC. And there alpha square is a characteristic surface of the different molecular elements which are broken one after the other while fracture progresses. So that's the general setup. And when this is, when you have something in alpha square over kBt which is very straight, then basically this kind of flow gives you something with either an enormous speed and an almost zero speed. So for a human observer at a scale of a few minutes, what you feel is something where there is either no motion at all or a motion with something that stays at delta G equal more or less to zero. So that's a quasi-static description of crack progress. But some processes which involve several time scales, because you get a large range of GC for the pinning thresholds, for example, or because you are interested in both the small time scales and the large time scales, require a good description of both the energy release rate, G, which contains the mechanics of the problem, and the quench disorder in the critical energy release rate, GC. And then they require a good understanding and a good description both of the quenched disorder in the material properties, the variations with space of the material properties, and the thermal disorder, the fact that if you wait long enough, something will be activated. And there, as we'll see in the second part of the talk, time and size and scales matter to know what's most important between quenched or thermal disorder to see how various modes relax. Now, in the experiment that was introduced 2 days ago by Daniel Bonamy, it's not the same experiment as the one he presented all the time, but it's related. That's not in polystyrene. That's an experiment which some of you might know because there's been a number of studies performed on that one already in the group of Knut-Jürgen Molloy. That's a mode 1 experiment in PMMA. So these are 2 PMMA plates in which disorder is introduced by sandblasting the plates. The 2 plates are put together under load. They are heated for a while, and then tension is imposed on the side, and a mode 1 crack is open and propagates. So this picture here is once the PMMA plates reopen along the pre-existing interface, you see the roughness of the crack, which diffuses, which multiscatters the light. So the appearance of through a microscope, the appearance of the system is not the same where it's open and where it's closed. So like this, you can do some treatment and look at the front of the crack and how it progresses with time, loading it either with a fixed, so it can be loaded at fixed velocities on the sides or fixed displacement, and you let it relax. For example, these are 2 typical modes of loading. And here we are opening the 2 plates like this, and this is progressing like that. This is the front that we extract, that space that's along the crack propagation. And what we looked at, among other, is you can either wait at fixed displacement, or you can load your system at various speeds. We explored almost 4 orders of magnitude in loading speed in this system. This is not, the crack propagation speeds are far below the Rayleigh speed. These are not elastodynamic, this is not the elastodynamic regime. And that's rather the kinetic regime. And if we plot the log of the crack velocity divided by V0, where V0 is 1 meter per second here, as function of the energy release rate that we compute for that geometry and the extent of the crack and the thickness of the plates, we know the elastic properties of our system, so we can compute the amount of total energy released per unit surface when the crack advances. So that's our energy release rate. What we find at large scale, I mean, it's also at large scale, we can compute the average energy release rate because at large scale, the crack is almost straight. Then the mechanical problem is easy to solve to compute this G bar. And what we find is this almost straight regime, you know, for energy release rates, which are somewhere around from 100 joules per square meter to 140. And you see that there's here a range in average velocity during a given experiment where we start to accelerate and stop, which is a factor 100 almost. From that's a log in base 10. And we find a straight curve. For the average, I mean, we expect this type of thing for the small scales, but this holds also for the average speed. Apparently, this scales up rather directly. And if we make a fit of this line, since we know what is the average, I mean, since we know G bar, here G is GC minus G bar. And from the slope of this line, we have this alpha square over KBTN. This gives us a very small, this slope here gives us a very small size, slightly less than characteristic molecular size. It's probably because we have projected here a 3D problem onto a 2D view. So there are probably several links that can break one after the other. But this number here is just something coming from that slope. And so one of our motivations for looking a bit more into temperature was to understand a bit better the implications of that for models of propagation of interfacial crack fronts. But it can be important for other contexts too. Now I come to the thing I will spend most time talking about today. That's fracture in paper, because monitoring the temperature in a thin object is easier than in a 3D object. So we did very simple experiments with paper, ordinary paper that you use in a printer or laser jet printer. And we have put our paper sheets under load, and we impose a displacement, which is typically a few tenths or hundreds of microns per second, usually rather tenths. And we have two parallel bars like this, and we start to pull over the paper with these two parallel bars. Our paper samples are 10 centimeters, typically 10 centimeters in size. There's a pre-cut in the middle if we want to avoid that the cracks start along the corners of the two metallical cylinders on the side. And we follow the deformation of our paper sheets, both with a fast camera and with optical camera and with an infrared camera to have access to the temperature field. It's an infrared camera that takes pictures at 150 frames per second. At the same time, we monitor the force, the total force imposed on the paper, and the displacement between the two sides. The crack propagates. The crack then propagates like this. We have usually a pre-cut. The room temperature and room humidity is kept fixed around 24 degrees C and 20% humidity, and we pull regularly. Since this is not a system with a dead load, if you do this kind of experiment with a dead load, what happens is that once your crack starts to progress, the average stress you have in the rest of the paper increases, and this is an unstable process. So suddenly you tear it up, and it starts to the end. This is not the same type of unstable situation, because it's not a situation with an imposed force. It's a situation with an imposed elongation. So as you will see, we have some times where there's a fast propagation of crack or creation of defaults. We see holes in the papers between the fibers, but then it can slow down again and start again. So it's really a type of creep process. If I want to do the type of experiments, that's the kind. That's yesterday's newspaper, and you can do this experiment yourself, but it's a bit hard to control the. We have a pre-cut, and it's a bit hard to control the force. But oh, okay. The pre-cut doesn't function. Yeah, what I have here is a system which is not nicely loaded with my two bars, but one of the things you notice when you do that is that you see little fibers from closely enough on the sides, which are stitching out, and you also typically hear a noise. When you look at it from close away, the velocity of the crack propagation is not constant. So it emits vibrations that you can hear. And so that's an instantaneous picture. So that's not exactly the same geometry. We started with two notches, then in the next ones that will be with one straight notch. But here you see the infrared images superimposed with the optical picture. So that's a zoomed crack. As you see, the crack object is not that simple because you see that there are still fibers which are going through. How cohesive they are is not evident because it's a 3D problem and you look through it. But there are still probably some fibers exerting some load here. And you have holes opening that you can distinguish with your optical camera. And typically some heat being produced ahead of what you can identify optically as a hole. So there are fibers which are being disentangled and friction happening between fibers before you make a hole which is sufficiently large to see through the 150 microns of thickness of your paper sheets. A single paper fiber has typically a length of 100 microns, or I mean somewhere in the range between 20 and 200 microns. This depends on the fiber. Yes?
What is the scale of that?
The scale of this is around 10 centimeters.
10.
So, I will show you. So here, this is a maximum temperature from what we see, which is around 3 degrees, or that's typically the range. At the scale, but that's a critical issue. This highly depends on how far you are and how much you zoom. But that's a few degrees Celsius. And so I say a paper fiber, typically it has a length which is some 100 microns or 200 or 50, and a thickness which is more in the range 1 to 10 microns. And that's the next. So that's the next step, and you still see these little fibers which are stitching out here. That's the fourth measurement during the same experiment. So that's time in seconds. You see a typical experiment takes a few minutes, and the fourth, so it goes up to there's a long linear stage after some initial maybe bending or something, which is maybe due to the fact that the paper initially is not totally straight. But after that, you get this straight regime, and there you start to break fibers. And here your paper is totally torn apart. You see that since the problem is rather stable, it takes much more time from the first fiber breaks to the complete tearing out of the paper. It takes almost 1 minute in that case. And you get plenty of large events and small events. That's the temperature in degree C. So that the rise of temperature with respect to time. That's the same thing, but zoomed. And you see that it goes up and down. That's just the hottest point that we extract from the higher field. The size of the pixels of our infrared measurements are slightly less than 1 millimeter, 0.4 millimeter, if I remember well. The physical correspondence on the paper of our pixels.
That is essentially a small measurement. It's not a fast measurement. Okay. It could be an average increase in temperature.
It's a measurement apparatus, so it averages over a certain spatial scale and a certain time scale. So the sampling time for the high-air camera is 140 frames per second. It's
small
on the scale of a molecular vibration. It's slow. Yeah, so it's the average of many molecular things. the spike will be much higher, and also it's also large compared to the size of the fibers, because we look at something which is almost 500 microns across, and one fiber has a thickness of not even 10 microns. So it's also the average of the temperature rise of many fibers in every pixel. That's the hottest pixel which is found in the image for a given time.
But the time is before the system, the cracks start propagating, right?
No, here, that's the time where it starts to propagate. That's the noise, basically, that you have. And here, around 20 seconds, the crack starts to propagate. Or at least you see a hot spot which is generated and starts to propagate. Then if you see a hollow part behind it that you call the crack,
But the size is still linearly increasing.
uh,
The same experiment you showed in the previous slide.
I think that basically you start to be somewhere here in this slow. When you start to go up in temperature, you are somewhere in this downward inclination here. Okay. Here I show you a little movie of the same thing. So that's real time, and the crack starts to progress from there. That's the maximum temperature. So there are fluctuations, just measurement artifacts. And here you see that there's the start of a crack propagation and a rise which is not even 1 degree C. Then you have some slightly faster one. That's a bit slow. Okay. So that's probably when you see the first peak, the first dropping of the force.
This time is in seconds?
And then you have something, yeah, that's time in seconds, here. And that's just a pixel, so for the physical size you need to multiply by slightly less than a millimeter, 0.5 or 0.4. And sometimes it goes faster and it goes down. And at the end, it will just go fast. In this experiment, it will just tear the rest out. Okay, and here, poof, you have something much hotter and it tears the rest. In some other experiments, it can stop after traveling 1/4, say, or 1/3 of the cell and start again slowly before eventually you get some that tears the rest. Yes? Yeah, in this one now you have just one crack. We have simplified. We decided that we did not want so much to study the crack tip interaction, but rather follow what we had. So then we modified the setup to have just one precut on one side and start from that precut which is there. Okay, so these are instantaneous snapshots of the same thing with a slightly different color bar. Time is here, so it rises like that. And you see that the temperature rise is bigger on this side. If you look at so you see also the position of you can extract the position of the hottest spot and project it along the x-axis like this, and then you get this as function of time, and you can derive that, and you get the speed as function of time. So the speed fluctuates. You get a rather low speed, which is typically a couple of millimeters per second. It vibrates around a few millimeters per second. And then there are some fast spikes which can be several centimeters. It can be sometimes up to 10 centimeters per second. That's the range of the. And there are these two typical regimes for the propagation of the fracture, and that's the displacement and the force, which is monitored. So from this force displacement curves, we can extract the total mechanical energy which has been put in the system. What I show you here, by the way, is published in a paper in Soft Matter last year. So then we are interested in evaluating the Joule heating per unit surface from the temperature profile. What our first goal in doing these experiments was to evaluate the energy budget of what happens. Basically to know in the energy we put in the system, how much goes into heating the system. We know, I mean, in this one we didn't have accelerometers on the paper, but we know typically that the energy emitted in this kind of experiments in the form of mechanical waves is not more than a couple of percent. It can be 1% or below or a few percent, but it's not the dominating factor. And we wanted to know how much the rise of internal energy that contributes to rising the temperature is from the total energy. And what we will find is that there's a correlation. I mean, what you saw already from the fact that the color of the spot is hotter when the fracture goes fast. It's the large Joule heating is happening at large speeds, and the fraction of mechanical energy that goes into Joule heating increases 3 to 4 folds during the fast propagation. So to have an idea of what the temperature profiles are, here I have cuts which are perpendicular to the average direction of propagation of the fracture. So that's close to the tip. The tip is here, or the red one. And if I look behind my front, I have things that become like this. So this looks pretty much like a 1D diffusion problem, where you deposit some energy close to the tip, and in the dimension perpendicular to the crack propagation, you diffuse away in the paper. These are basically Gaussians. And if we look at the integral of the Gaussians at some distance, or it's not actually at some distance, we transform the distance into a time since the crack has passed in this direction. So if we look at the integral of these Gaussians after sometimes the crack has passed along this profile, we have something that decays, that's log and time, so it decays exponentially. There's basically some cooling, which we model as cooling into the air, into the neighboring atmosphere. And from this, so I'll give you more details afterwards, but we can compute. So that's the velocity as function of time. That's here's the energy release rate, and here what we have is the quantity from the quantity we had, which is the integral under the Gaussian. We can extract how much heating has been transferred into the system, and divided by the area of propagation of the crack, and from that we get the internal energy rise per unit square meter, so Joule heating per unit surface, and it goes up significantly when the crack goes fast. Here it's an experiment where the crack went fast and stopped going fast again. So by dividing this by that, we can have a ratio of how much of the mechanical energy release rate goes into Joule heating, and we find that it goes up when the crack goes fast, 3 or 4-fold. That's just to have an idea of just representation of the deformation during the experiment. So we did some digital image correlation. We have put some little spots on our paper to identify it easily. So the color here is proportional to the displacement in this direction. And we see the crack on top. And we see something like that. It's just saturating behind. And you see the crack, which is wiggling a little bit. From that, you can compute that's epsilon yy, the strain in this direction, but we don't really exploit that because we don't have a resolution which is good enough to see any singularity close to the tip. So it's more for fun. And the way in which we understand the process at the simplest level is by saying that the heat is produced in a zone of size L around the tip of the crack, which we model as circular because we don't really know exactly the more details than that. So we have a characteristic size L, and we say that, okay, most of the energy which generates internal energy rise is dissipated in that process zone. And then there's a diffusion which is in the plane, the diffusion of the temperature rise in the plane and out of the plane. So from that, T is our temperature, the partial derivative with time, which is T. Rho is the density, C is the specific heat per unit mass. And here we have a Fourier law for the diffusion. That's Laplacian in the plane. And since normally what you have is a 3D equation, you have a 3D equation where that's Laplacian in 3D. But what we look at is a problem in 2D. We checked by heating our entire paper sheets and looking at how they cool down that the Laplacian term that we have in the other direction and the way in which the temperature the paper cools down in the surrounding air is that's a classical behavior where basically the temperature relaxes towards the reservoir temperature, in this case the air, with a certain characteristic constant 2 gamma over h. So this is the missing term in the 3D Laplacian that just corresponds to some loss of heat into the surrounding air proportional to T air minus average T across the sheet. And here we have W, our production of heat, due to the crack process.
What is gamma?
Gamma?
Yeah.
So this gamma here depends really on the coupling between the paper and the air. So if you have the surface of the paper, which is at a temperature slightly different from the air at some distance, there is a decay of temperature in the air that can depend on the particular conditions, you know, the relative humidity, and you should avoid having too much air motion and so on in your system around, because that will affect this gamma. So what we do is that we calibrate it by measuring it in experiments where we heat the paper and we let it cool down, and we look at how initially homogeneous a paper with a homogeneous temperature is going back towards the room temperature, and it does that in an exponential way, which gives us an estimation of this.
Because you have on both sides. Factor 2.
The factor 2 is because we have two sides. Yeah, there's nothing important in this factor 2. And then the equation to solve becomes this. That's just the expression of W. Omega here is 1 in a little disk and 0 outside. Alpha is the fraction of the energy release rate that goes into heating. that we try to evaluate. V is the velocity of the crack, and that's the area of the disk. So that's our source term. We can divide by rho c and have this with a certain characteristic tau. We have the heat diffusion constant of paper. We have a characteristic time for the loss into the atmosphere, which is that, and a prefactor of the source, which is this kappa here, alpha GV over rho c. When you do that, there's an analytical expression for there's an analytical expression that you can find. You can transform you can transform this you can transform this actually by multiplying by exponent. Here you have a linear first order equation. So you transform this by multiplying t by exponential of t over tau.
Sir, can I ask? Omega xy, I mean omega of x comma y, that is the dissipation.
Yeah, so that's just a
why
geometric.
Function of time, omega xy t, you're taking it as scaled by velocity.
Yeah, that's just if I want to compute that omega here is a Heaviside function. So if I want to compute how much I know how much energy I put per unit area. This energy per unit area is alpha g. That's my assumption. And then from the experiment, I want to evaluate alpha. And if I want to know how much surface I go through during a unit time, I have to multiply this by the velocity. The total surface you go per time unit will be proportional to the velocity of the crack. Okay? So that's why you have V. And then there's an expression for what you have in there's an expression for what you have if you have just a Dirac, if you reduce omega to a size 0, then you have an analytical expression for the solution, which is this. Delta T goes as a, well, it's a diffusion problem with a motion. If V is constant, you, even if it's not constant, it will just depend on Tp of x, the time where you went, the time where you were at a given position at x, and you get an expression like that for the result. That's the field which is represented for the temperature behind the tip with the Dirac here. And then we just noticed that, where is it? Okay, I have not put the details there, but basically we have noticed that in these expressions, the contribution of in the gradient of the contribution in the Laplacian of the gradient along the crack propagation direction is much lower than the contribution transverse to the propagation direction, which corresponds to the fact that these lines here, the iso temperature lines, are more or less straight. So since they are more or less straight, it means that we are basically in a 1D type of problem. So if we do that, then we find that if we define integral of temperature across profiles like that, we have this here in profiles like that, we have the type of Gaussians that I just showed you before, which are well followed both by the experiments and 2D simulations. And then when I take profiles like this, what I have is that this integrated temperature rise along profiles like this are simply decaying exponentially with time. They are equal to alpha g over rho c and times exponential of minus t minus tp over tau, where tp is the time where the crack passed at the position you look at. So by looking at these integrals and knowing when the crack passed along this line, I can evaluate how much energy has been deposited along this line. So that's what you have here. That's, these are the spatial representation of the thing, but if we average over some time windows and go into the reference frame of the moving crack and represent things not as function of space on both sides, but space like this and time since the crack has passed like that, we have a representation like this. Time since the crack has passed, and y with y equals 0 corresponding to the tip position. We average this over little windows. Like this, we have a clearer signal. And what we found is this. These are basically Gaussians that are becoming larger, and the integral is becoming smaller. So by evaluating these integrals, we go back to time 0 and we evaluate I0. We just suppress the part corresponding to the loss into the surrounding paper, and we can evaluate how much we can evaluate what we're interested in, which is alpha G over rho C, so alpha G. And this I0, which is alpha G over rho C, we get an expression that's for most of the experiment. We get an expression like this, and during the fast stages, we have values which are, you see, that's that's Neparian logarithm, so that's 3 to 4 times higher when it goes faster, the energy that we see. This corresponds to this corresponds to this thing, and alpha goes up as well. And that's the typical result of numerical, direct numerical simulation of that equation. You can play with the parameters of the size of the process zone. In the far field, it doesn't change anything. It only changes the temperature you have close to the tip. But what we noticed is that, so with a smaller dissipation zone, of course, instead of rising, that's with a dissipation zone which is a few tenths of microns. But when you make it slightly smaller, you can start to rise your temperature much higher, several tenths of degrees, or even exceed 100. And if you look at the same process, but with pixels which are, that's just to illustrate that if you look at the same process which are pixels which are 400 microns, and you average the temperature over the size of your pixels, you don't detect that's what you said. You don't detect the very large peaks. You detect something which is much smaller, a couple of tenths of degrees, even though you have a little spot in the middle that can be 10 micron size, which is more than 100 degrees in temperature elevation. So that's a better simulation with a zoomed out version, and that's so that's with a process zone of 10 microns. The center of our crack that moves at a fixed speed of 1 centimeters per second, it's here. And there you see that the temperature starts to rise at the tip of the process zone, and on the back of the process zone you have the temperature which has risen very significantly. In this case, what we find is that when we go down to process zones of size 10 microns or smaller, that's not the case if we use process zone size of 50 microns or 100 microns, but if we start to use process zone of the size of around 10 microns, you reach a temperature in the back of the process zone which is, you see, close to 200 degrees. And that's a temperature for paper. So that's just in a very tiny zone on the back of the process zone. So this thing here is really a fraction of micron, like half a micron. But characteristic temperatures like that actually are sufficient to start to oxidize paper. That's, you know, Fahrenheit. If you remember Ray Bradbury, that's Fahrenheit 451, yes?
Yeah, essentially, I mean, this could be also a consequence of the Fourier law.
A consequence of?
A consequence of Fourier law. Fourier law, if you go backwards, you always get to a divergence.
Yeah, there's a divergence. So the size that you, the maximum temperature.
Is in your equation automatically.
It is automatically in the equation, simply that's the solution of the green function of diffusion. I agree. I'm just saying that if I want to, now I have several lengths at play in a material like this. And if I use a length which is not the length of the fiber, but the thickness of the fiber, then I just notice that for the characteristic of paper, this gives me a temperature which is able to trigger over a very tiny temperature which is enough to trigger a chemical reaction. But there's nothing mysterious. That's just the properties of the singularity of the diffusion equation. Yeah. And this maximum is smoothed out, the singularity is smoothed out by the finite size of the process zone. Yeah. And then if you assume, so this depends on the speed. If you assume that the velocity then if you assume that if you start to release energy like this on the back, then you can compute what is the thickness of the size where you reach this characteristic temperature. And when you multiply this thickness by the energy of the reaction per unit mass of transforming cellulose, then you find an extra energy that goes into your system, which is energy that your chemical reaction releases. And this extra energy is of the order of magnitude of the rise that we see in the internal energy when the crack goes fast. So that's the first thing that tells us that maybe there's an extra energy source when the crack goes fast, which is related to this kind of reaction. The second evidence we have that this might happen from time to time is that if you have a characteristic size L and you have a diffusion process, then if when your paper heats, the fibers get softer and it's easier to disentangle them, then you will have a time which is set by how long it takes to diffuse through the process zone to send the energy which is created on the back into the front. It will take a time that goes as square root of L over T, and then you can transfer this time with again the size of the, when you divide L by this time, you will have a speed, for a characteristic speed for the advance of your crack, which comes from the diffusion equation and the size of the fiber that you have, which will be 4D over L. And that's also of the order of the fast, but using the thickness of the fibers and the diffusion of heat in paper, you obtain something which is characteristic of the fast stages during the fast avalanches in paper. So you can also evaluate it numerically. These are the points we have. You can also look at approximations for what you expect for the maximum temperature behind these profiles. We get 3 regimes, and if we play with velocity, so these are analytical expressions and simulations, if we change the velocity of advance of the crack, we find different rise of temperatures of the back, and if we start to go around, centimeter per second, we go into a regime where on the back we reach the oxidation temperature of the paper. So Yeah, I just see what time it is now. I have basically another thing which is, the rest is another topic, which is about how you can modify, how for interfacial fracture you can modify the equations which are used for elastic line propagation into something where instead of putting velocity which is proportional to g minus gc, we replace that by an Arrhenius law, and by then putting a disorder in gc and elastic interactions in the front, we see that putting this Arrhenius law and taking into account that we have a process which is not only at velocity 0 when you are under gc, or at velocity proportional to g minus gc when you are above, but rather replace that by this kind of, by the nonlinearity you have in an Arrhenius law. You change actually some of the, you change, for example, the roughness of the crack fronts, and you find different small scale and large scale regimes, and you can compute, you can compute how these, the small scales and large scales relax, but that will be too long, so I think I'll stop with the paper story here. Thank you.
There was some work done by Rice long time back in 1970s, Levy and Rice, where
Yes.
they published something very similar to this. Have you tried comparing your radical solution with that?
Yeah, well, what Levy and Rice did was, I mean, the solution of Levy and Rice is this, but without the T minus TP, because they consider the system where it's not a 2D system where it cools into the surrounding material. So they had a solution like that, and they looked at, and then it was just it was a purely numerical analytical work where they assumed that the total fraction of the energy released goes into heating, because I mean, you have to do assumptions if you don't have measures. So they computed how hot, yeah, they applied that to, I think, metallurgy problems, trying to compute what they expected as a heating of the cracks. Here, since we have measures, what we do is that we compute and we compare. So our alpha here, the alpha that we get, I forgot to tell you, this one doesn't depend on the process zone size. It's an integral thing, and we find that it's usually around 10 to 15%, and it goes up to almost 50 or 60% when the crack goes fast. So the initial motivation for these experiments was to compute this alpha. First, it's interesting to know that it's just, you know, a couple of tenths of percent, which means that the majority of the energy during the process, contrarily to the hypothesis of Levy and Rice, but that was for another material, so they might be right in that material. But in this material, at least, the majority of the energy does not go into heating the system. It probably goes into creating dislocations, micro defaults. Basically, most of the process which happens here is that you disentangle the fibers, and usually you have a process zone which is large. You rise a few degrees, but from time to time in your net of disentangled fibers, you have just two untangled fibers. It's too long, and you don't manage anymore to disentangle them by friction along them, and you have to break a knot. And if you start to break a knot, you can have then you can actually the yield strength of cellulose, if you need really to bend the sides of the cellulose balls, it's much higher than the typical yield for friction between two fibers. And then you can reach much higher stresses and have a much smaller size. But most of the energy here goes into create.
The work is for metals. I mean, basically, it was
This was metals. Yeah. So I don't know in metals what fraction goes. They assumed it was alpha equal 100%. Yeah. Okay.
There is some sound associated with
So in this experiment, we did not measure it. We measured in other experiments, but the next step is to redo the infrared measurement at the same time as we monitor exactly the energy which is put into the, which is how much energy goes into radiated mechanical energy. But we already know that from other experiments that typically it's even under this Joule heating. We will be very surprised if that's not the case in these ones, because in other experiments with some also ordinary paper, it was more of the order of a couple of %.
With the Arrhenius law, experiment in DNA, can't we imagine, so you say that you keep GC constant and place the slow velocity dependence in the Arrhenius law. Can we not imagine that GC itself would depend on quark velocity, and because of the scholastic effect and the fact that tracing and disentangling the polymer shapes takes more and more energy as the quark speed is increasing, and could it also explain this kind of things?
I mean, for me, GC is a material. What depends on you have a dependence between G and V, which is, like you say, there's. I mean, if you compute what is, for me, GC is a material parameter. If I associate it to how much energy it takes to go over an energy barrier, I know that I will go at different. I know that I will have a G. I will find a G for my crack if I measure the G, which is not the same at different speeds. But the GC I have is associated to a certain process. So it could go that it could be that what you tell me is that you could go through a different path, have another barrier that you explore when you go at a different speed.
Maybe another explanation to say that without involving Arrhenius law, is saying that so we have a quasi-static crack, except that so at every time step you have G is equal to GC, except that GC now depends itself on V.
But what we found also doing direct simulations of this process in models is that if we assume that we have an Arrhenius law at small scale, we recover it at large scale. This goes up through the scales. I'm not saying it's the only possibility, but I mean, creep laws are usually of that form for where if you go down slowly. What we did in these experiments is that we explored 4 orders of magnitude in speed. So and we find this slow dependence on GC that we have, and then just directly looking at if we assume that there's a certain characteristic GC level, which is the same for all the speed, then we observe. Anyhow, that's just an observation. Here we don't assume any Arrhenius law. Here that's just V as function of G at large scale, you know. So I'm just observing this is an exponential. Then you tell me maybe in fact maybe in fact I have always G equal GC, but everything is into. I'm just saying if I put GC equals a constant, this has the same shape. Now you tell me that maybe GC does something complicated and G does something complicated, but I'm.
Dependence of GC on V kicks in at higher velocity. The velocities are very small. I mean,
Well, these velocities are
meters per second.
these velocities go from a few microns to centimeters per second will be the very large range. That's
From my understanding, that kicks in at much higher speeds.
So you shown that if you plot the movements of the rats, after some time it will move faster. So is it possible to predict this time?
so first it goes not too fast and then it goes faster.
Yes.
Is it possible to do what?
This time after which it is moving faster.
To predict this time. We did not try to predict this time, and I think it's probably related to the mechanical properties of the fibers, to the particular structure of the paper. Because when we do the experiment twice, it never happens exactly at the same position. Even sometimes it happens at the third of the experiment, goes fast, stops after 1/2, goes slowly, starts again. So I think it depends on the small scale disorder in the paper.
So, in your diffusion equation, where does the thickness of the paper in this time?
The thickness of the paper enters into the fact that I know what is the specific heat per unit. I know what is the specific heat per kilogram of paper. This is measured, and then if you ask what is the mass per unit area of paper, you have to integrate over h. You need to heat up a larger piece of paper. But at the same time, you have a cross section of the crack, which is also larger. So this cancels out. What you have after that is that I think the loss term, the loss term into the surrounding atmosphere, it's normally the flux of heat into the atmosphere is proportional to the surface and the temperature difference between the surface of the paper and the temperature in the air, slightly further away from it. So then when you compute how much heat you extract from the paper per unit surface, you will have h. You will have the thickness that plays a role there. So I think that if you take a larger, a thicker paper, it will probably take longer before all the heat gets out. If you heat it up, it will take longer before all the heat gets out into the surrounding reservoir. That's where it enters. So that's why you get 1/h here, actually. That comes from the gamma you have here is just for the flux at the surface, and when you divide that by the thickness of your paper, that's where it enters. But we have just used, we have not systematically varied the paper thickness. So I just know that if I take a thicker body, it will have an internal energy proportional to its thickness for a given temperature.
Can this experiment be related to fiber bundle model?
It's probably possible, but it's quite complicated fiber bundles. Some people try to do that sometimes in the paper industry. but these are fibers that are, I mean, it's not just two plates. A fiber bundle model usually is an idealization of systems like this or others, because here you really get a lot of friction between neighboring fibers, even some cohesion. So I think yeah, if you make the geometry of your fiber bundle model sufficiently complicated, that will reflect the friction, you can. If you have?
Textured paper with fibers.
Well, all papers are always slightly textured by the fabrication process. The fact that you tear out a bunch of cellulose fibers out of glue orients the fibers. So the look of a crack, if I do this, or if I do that, and I have a look at the details of the crack, there's one orientation with hairs which are a bit larger. Basically, you don't get exactly the same prefactor for the roughness and the same length of fibers that stitch out, depending on whether you break along the fibers or perpendicular to the fibers. So papers are textured.